joined up debugging analysis in the RISC V world. So my agenda is I'm going to make some obvious statements. Hopefully they're not going to be too contentious. And then I'm going to give a requirements list of what I think we need for providing visibility and analysis of SOCs. And then I'll run through some examples of performance analysis and debug. And then finish up with some use cases, and then I'll hopefully show a slide of the demo that we're going to show at the poster session. It won't be as impressive as the Sci-Fi one. I haven't got Doom, but I've got some very snazzy circa 1990s state-of-the-art Mandelbrot sets. Okay, some obvious statements. I mean, SOCs have become increasingly complicated, and they're not going to get any simpler. These contain several processors, usually from different vendors, sometimes have hundreds of silicon IP blocks that contain complex interconnects. You throw in the software has been created by a large team who disperate across the world. And all this has to work together. So what I'm saying is that debugging of these complex SOCs isn't just run control. It's not just processor-centric run control or accessing instruction trace. These are important, but I think what is required is having visibility of the whole SOC. I would claim that what we need is a vendor-neutral debugging structure. Now, what I mean by that is that it's not tied to a particular processor core, not tied to a particular graphics engine. The one that allows not just run control, visibility of what's going in the processor, it also allows visibility of what's happening on the interconnect, on some custom logic. We need to be able to have these debug entities that are fit for purpose. You configure them at RTL time for your instantiation. The cross-triggering between these blocks are done as part of the whole infrastructure, are not separate signals. And the cross-triggering is a runtime configurable thing, not hardwired at RTL. We need to have security built in. What I mean by that is access to the SOC through a debug port needs to be secure. And importantly, we need to have this for the whole development flow. This means from simulation to emulation to FPGA and in real silicon. Because I think the value of this is observing, providing visibility of what's happening in the target SOC in the field. So UltraSoC, so we're a VC-based company, a VC-funded company based in Cambridge in the UK. We're members of the foundation, and what we provide, you might have guessed it, we provide silicon IP and tools that helps with visibility of the SOC, usually in the field, but as I mentioned, the IP is soft and it can be used throughout the development flow. We have a number of partnerships with IP vendors, Imagination being one, Siva. We announced CodaSip and Bassand earlier today. And we have some partnerships with tools vendors, again, Siva and Lauterbach. The IP that we have has been used by a number of customers and for a number of years, and we've just announced some recent design wins not so long ago. So it's silicon proven, so it's not a concept. It's been used by companies for the last 6-7 years. Okay, the principles what we have is, as you guys know, a target SOC usually has an interconnect of some sort. It could be a network on a chip, or it could be conventional AXI-like type interconnects, or even your own. Hanging off that interconnect, you have a bunch of processors, graphics engines, DRAM controllers, security engines, and so on. And so what we provide UltraSoC that is, we provide 3 classes of IP. The first class is a bunch of analytics modules. The first obvious one is the runtime control, run control for a processor. This is your classic breakpoint setting, starting, stopping, going, looking at debug state of a processor. Then we have a bunch of others, and 2, the more complex and more important ones are things like the bus monitor. A bus monitor that we have are protocol-aware bus monitors and transaction-aware. So it understands the underlying protocol and tracks the outstanding transactions in flight. And we also have a similar sort of thing for conventional signals. We call that the status monitor. The second class of IP we provide is a message passing infrastructure, which is completely independent of the target subsystems interconnect. And the third class is a bunch of things we call communicators, which communicate with the UltraSoC domain to another domain. What I've shown here is just the USB communicator, but we have a bunch of others. JTAG is the obvious one, streaming SerDes, single wire, and indeed talking to conventional on-chip interconnect, so a subsystem on chip. So the way this stuff works is that we, at runtime, send messages into our UltraSoC domain. We configure the monitors and the analytics subsystems to observe for conditions. And when those conditions have been met, we either do local metrics calculations and then when certain times have been expired, we send that metric across a message passing infrastructure off chip via a communicator. We can configure the monitors to look for certain conditions like duration of a transaction, delays in being accepted on the bus, capture trace, and when certain memory accesses have been taken place, we can have 1 or more monitors sending cross-triggering messages across our message passing infrastructure to other monitors. So we don't have dedicated wires just for cross-triggering. And we also have the ability to assert signals from our message passing infrastructure, so internal signals tied to internal GPIO, excuse me, tied to internal GPIOs. So what we have here is effectively 2 systems in one. You have your target SOC and you have a monitoring subsystem. The 2 are independent. The monitoring subsystem is non-intrusive unless you design it to be intrusive. Classic case is the run control, which by definition will be intrusive. So I think in order to give you an idea how this stuff works, I've got some examples of what I would want to see in an SOC that I might be designing. In a previous life, I designed modem chips. So not surprisingly, my examples are based around that. So if we take a sort of candidate software-defined radio, which contains a radio subsystem, a DSP subsystem, and a couple of scalar processors, the sort of light blue colors, the SM is the status monitor, the BM is the bus monitor, and I've collapsed the message passing infrastructure into one block. But I'll show you later what it actually looks like. So if I have such a system, we can ask questions like this and provide answers for them. So for example, what's happening in my CPU to prevent the performance I'm supposed to be getting? Why do some DMAs take so long? What's the mismatch between the DSPs and the host software? And why do my systems sometimes deadlock? So let's take the bus monitor here at the bottom left, which is attached to the dual port DRAM controller. At runtime, I can configure that bus monitor. Now remember, it's a protocol aware and transaction aware. I can configure that bus monitor to count the number of transactions coming from the iCache port of that single processor. Count the transactions in a window of time. When that window of time expires, send that count off, and then continue. So over a whole duration of the run of this software, I can get data on a regular basis and plot a pie chart like this. Now this tells me 80% of the time I see no iCache misses. 12% of the time I see one outstanding iCache miss, and 8% of the time I see two outstanding iCache misses. Now remember, this data has been extracted while the system's running in the field. So from this data, it tells me 8% of the time the branch predictor is mispredicting. So that tells me that I can get my compiler writers and my system software guys to provide better hints to the branch predictor to try and eliminate that 8%. But also, I can experiment with placement of code. Because this is being done while the system's running, I can experiment with my placement of code to try and reduce the 12%. So I can check on a regression basis what it looked like from yesterday or last week. So this way, your quality engineering team can have a visibility of how your software is performing in the system designed today. This is using the same bus monitor, but this time we're going to look at iCache misses from 4 of the processors. I'm telling the bus monitor to look for iCache misses from these processors, from the iCache ports. Of course, I'm using iCache because you guys know if you miss, you stall, which means you lose performance. On a long window, in a big window of time, the total iCache miss rate is about 600 megabytes. But I'm telling that bus monitor to look at iCache misses in a window of time. And as you'll see, that red window there, all the iCache misses arrive at the same time, which means instead of 600 megabytes, you have a window where 2 gigabytes worth of accesses have been made to that DRAM controller. For something like a LTE category 12 LTE modem, you're looking at about 1 gigabyte from the turbo alone. So very quickly, you've got 3 to do. You're starting to push the limits of a sort of consumer device DRAM controller. Now, clearly, if that window is small and doesn't occur very often, it's not a problem. But if the window is sufficiently large, you're going to have serious problems. This is information that's been gathered in real time, and the bus monitor is sending out the metrics periodically. Remember that the bus monitor is protocol aware, so we can look for things like deadlock. So my definition of deadlock here is a transaction, a request goes out and the response either takes a very long time or never comes back. So we can configure the bus monitor to look for this condition, either from a particular master or all initiators. We can configure how long a very long time is, and we can take a number of actions, such as capturing the trace in a circular buffer to find out what led up to that transaction deadlocking. In fact, one of the demos we have shows just this. Again, with the bus monitor, we can look at exploit because it sniffs the traffic going on the bus. We can look for certain classes of data corruption. So we can say initiator 1 here has some data structures in memory which get corrupted by some other initiator. So we can configure the bus monitor to look for accesses to that region of memory. And if it isn't initiator 1, then we take a snapshot of that transaction. Everything's timestamped so we know when it happened and who did it. We can use that event message to either halt the whole system, stop the processor, or inform a debugger this has happened. The pseudocode is just that. All this is done in hardware. We don't have any CPUs running in the bus monitors. So I'm suffering from the PDF issue here as well. This was supposed to show a status monitor is attached to the PMU of one of the CPUs. The status monitor is periodically counting the number of stall sequences it sees. And when the window of time is expired, it sends that off across our message passing infrastructure. And in this case, it goes out off chip via our debug hub. And the intention with that is you can plot a chart like this to see what the stall behavior of your whole system is. This is just for one processor, but you can do this for a number of processors too. In this example, this is to show that our cross-triggering can be used to help reduce the amount of traffic. So in this case, the customer is only interested in observing instruction trace coming out of the processor when a particular condition occurs. And the condition is that when one of the CPU, non-CPU masters up in the top left hand accesses a region of memory, it causes a stall in processor A, but the customer wants to see the instructions that processor B is carrying out when that stall happens. So what happens, let's go back, the bus monitor A, we configure that at runtime to look for accesses to that region of memory. When that happens, it sends a cross-triggering message across our message passing infrastructure to the status monitor here, which looks for the stall signal of processor A. When it sees that, the status monitor then sends us a cross-triggering message to the trace receiver of processor B to start receiving trace. And of course, what that means is instead of having shed loads of trace information coming out, as on the left-hand side, you only get to see the trace that you're actually interested in. So the key features that we have is that this is non-intrusive unless you design it to be intrusive. The monitors are smart, they have lots of local intelligence, and they do lots of metric generation. So you're not blindly sniffing and sending off transactions off the bus and therefore hitting your bandwidth off chip. The bus monitors themselves are protocol aware, so we have bus monitors for most of the bus protocols out there. The run control that we have, I think we have run control for most processors, including RISC V. Our interconnect is a message-based protocol, and it allows for cross-triggering and data in the same protocol. The status monitor that we have is an 8-stage logic analyzer and with trace capture and cross-triggering. We have a secure route into the debug monitoring system, both authentication and encryption, which I'll highlight shortly. And if you think about it, we have this monitoring system is observing the underlying target system. So we can set up conditions to look for example, certain events have taken place that shouldn't happen, or certain events should take place that haven't happened. So we call that bare metal security, because it's all done in hardware. The conditions for which the system is looking is runtime configurable. So a bus monitor looks a bit like this. We sniff at wire speed. So our lead customer, the wire speed runs, AXI bus runs at 1.3 gig. We sniff at wire speed. We do a whole bunch of matching, counting, metrics generation, and trace capture. So RTL time, you can specify how many matches you want, how many counts you want, what size counts are, whether you want to capture trace or not. And if you want to capture trace, how much buffering you want. So all these lead up to how big the bus monitor itself will be. So these are all knobs you set at RTL time, and depending what level you set it at, you get different gate counts. And so this is what I meant by fit for purpose. So certain parts of the chip I showed just earlier, you'll have a slightly less rich bus monitor as opposed to the dual ported bus monitor by the DRAM controller. You'll have the knobs set up higher. The status monitor takes in general generic signals in, and you can set at runtime what those signals mean and what to do. So let's just run through one example. So the top left-hand one, you guys know that those 5 signals have special meaning. At runtime, you configure the status monitor to look for, say, when the top red signal goes high, capture the 3-bit black signals, because you know that's a 3-bit bus. And then when the second red signal goes high, then send the trace out. So that's a case of 2-stage logic analyzer. So one of the other key things we have is that we have a USB hub communicator. So it's a proper hub. It requires no software resource from the target subsystem. we implement the MAC, the protocol, and the buffering completely in hardware. And so the laptop here on the left, on the right, will see two devices. It'll see the UltraSoC domain and then the target domain. So the security, I mentioned there's a secure route into the system. So, and I also showed earlier the message passing infrastructure is one humongous blob. It isn't. It's built up of message nodes or message hubs, and each route of the node, the tree, we have, again, RTL time, you can specify to have an access controller. And that access controller will do mutual authentication and will support encryption and decryption. So this way, you can secure data going off chip, decrypt it on chip, do whatever you need to from there. So this way, you can allow access to certain parts of the chip for certain phases of your development and exclude others. We have a bunch of blocks. I've concentrated on 3 or 4. There's about 30 modules ranging from all the different bus specs we know about. We have static instrumentation. We have different kinds of instruction trace modules, which we use to send the trace across our message passing infrastructure and ultimately off chip. We have ways of streaming information on chip memory for pulling out later. And then we have different sort of scenarios of message infrastructure. So in summary, I believe UltraSoC provides a complete advanced universal analytics and debug platform. It provides visibility of the whole SOC. It's non-intrusive unless you design it to be intrusive. And we're vendor neutral, so we're not, lined up with Siva or Tensilica or ARM. We provide access to all those processors. We have a novel way of getting in and out of the chip with a USB hub, but we support other routes of coming in and out of the chip as well. It's silicon proven. It supports, we have concepts of low power and power domains. So if you have power domains in your chip, we can save state, put state back when you bring the powers back online. And just to add, I think what we need to close, and I think this was discussed earlier, we need to close on the debug interface for the RISC V, because some of our tool vendors that we're working with are waiting for that to settle so that they can provide industry standard tools. And then I think a spec on the instruction trace would be very good. And that way we can support it too. Okay, just to quickly wrap up, I see these are the following use cases for this. So the first use case is your classic debug. This is a snapshot of our IDE, so the Eclipse-based IDE. You've got on the left-hand side is your classic project. There's source level debug in the middle. And whilst this is happening here, on the right-hand side, we're getting data from our monitors in sync, timestamp with code running on the processors. The other second use case I see is in field. So this shows a mobile phone, but we have a large customer in the Far East who makes TVs, and they want to be able to see the behavior of their video codec, very complex video codec in the field. So they want to be able to plug a USB cable into the back of their telly because they conveniently have USBs sockets, and then they would run a Python script, in this case a Python script on their laptop, to get some information like this. This is just showing the bandwidth coming out of the video codec. The third use case is this is hanging off the network somewhere, and then you route all this information, either security breaches or performance information, to something hanging off the other end of the network. And the final use case I see is it's completely standalone, and you have a dedicated analytic subsystem on chip. So either for looking for security breaches or monitoring performance as the system's running and reacting to it. In fact, we have a customer that does that at the moment. And I hope you guys are going to be around later at the poster session, because we'd like to show a multi-core RISC-based demo with real traffic and bus monitoring in real time. So thank you very much.
Awesome. Any questions for Gaj?
Hi, Sean Haller with Intensivate. So I guess two questions more on the interaction side. So with this infrastructure, if we want to put this into our chip, how close of the interaction do we need with your engineers? Is this low level, or can we, you know, in best case, just throw it over the fence and you instrument the chip after we're done?
I'd like to say the latter, but it's not. And we're a small startup. So what we do, it's soft RTL. So we deliver that, and then it becomes part of your design. So in the case of a bus monitor, you would need to decide which channels, in the case of AXI, which channels you want to look at, what parts of the transactions you want to look at, whether you're looking at all the address, etc., and then you would tie those into our bus monitor. I don't have a tool. I'd like to say I have a tool that does this automatically. I don't.
Right. So the follow-up to that is, how early in the design process do we need to get in touch with you to make sure that we're doing things in a way that are compatible with adding your infrastructure?
So ideally, when you're doing the architecture phase, but we have customers who come in late, and so you don't have to instrument everything. You can just do small subsystems. And so this one particular customer was too close to tape out, and they liked all the debug features that we had, but they wanted the equivalent of the fast access into their chip and access to their debug logic. So the infrastructure that we have lets them do that.
Thank you.
Can a customer write their own monitor to fit into your system?
So for a bus monitor,
bus status monitor, whatever, they have some piece of IP on which they have some specific measurement that for which you don't have it already created.
Sure. The answer is yes, of course. The bus monitor is constructed that
you have some interfaces that you can give them by which they can plug in their own monitors.
The bus protocol specific bit is a shim. The diagram I showed earlier about the trace and the counters and the matches, they're generic. So the shim would be taken away, and you'd write that.
Okay. Second question I have is that you have all these monitors that are sending stuff through your fabric out through your communicator.
Right.
How do you know you can keep up with the volume of data that's produced?
It's a very good question. So that's, if you're blindly just sending stuff off chip, then you're going to hit a bottleneck. It's like you'll always run out of memory.
What's the symptom there? You drop back?
So the protocol that we have, because it's all message based, we have information that says we've dropped packets. Yeah. You have a choice. You either drop packets or you back pressure. So this is all configurable. There's a quality of service. You drop one flow instead of another.
Okay.
So I've just highlighted the principles, but the detail is a little more complicated than that.
And finally, presumably for different customers, they will have different needs for how you observe the data, because the data might be specific to their particular chip, right? So
absolutely.
So you customize that for each customer, or?
So we started some of that with the IDE. So the graphics thing that you saw. Thing on the right, which you can't really see, that's a plugin. So basically you're getting data off the chip in the form of messages, which you have a viewer. And in this case, we've got a very simple, naive viewer here. In the case of this customer, this is providing messages, and we provide an example. This is how you view it.
If we have time for
we're running low. But yeah.
Okay.
gone. Okay.
Okay.
Thanks, Gaj.
Okay.